Hello, welcome to section 1.3, where we're going to look at vectors and things you can do with vectors, like take linear combinations of vectors and see what the set of all linear combinations of vectors are. But we'll see what all this means in a little bit. First, we just need to talk about what a vector is. So suppose you have any point in RC. R to the power C means that you have a list of C real numbers. I don't know how many there are in between, so that's the dot, dot, dot. Now, we can think of it as just like a point. Like, for example, here's a R2 in this picture. So the point 1, 3 right here is a point in R2, but we're also going to write it as a vector, which is a matrix with C different rows and one column. So a single column matrix is called a vector, and yeah, we can write it as just X with a little arrow over it. So we can tell it apart from just like the real number X. Okay, so the column matrix, this vector 1, 3, means the same thing as the point 1, 3. And sometimes we're going to think of it as an arrow, like the arrow that you draw from the origin that goes to that point. That's another way of thinking of the vector. Sometimes you can think of it as like the same arrow, but moved somewhere else, like over here or over here. This arrow's always the same arrow wherever you draw it. So especially in physics, they tend to think of vectors as arrows that way. Now, yeah, this is a special point right here, the origin, which we write as like 0 with an arrow over it, or just 0, comma 0, or as a column vector 0, 0, like so. But don't go overboard with the notation. If we have a single row matrix with C columns like this, that is not the same thing as the vector that we're talking about. Okay, so vectors are lists of numbers, but you can also treat a vector sort of as a number itself. Like if you multiply a vector by a real number k, you just multiply each of the components by k, like so. And you can also take two vectors, as long as they're the same size, as long as they both have the same number of entries in them, then you can add them together by just like adding u1 plus v1 to get the first component of the new vector, and so on with the rest of the components. Now let's take a minute to just think about the huge number of applications across science, technology, engineering, and math that vectors could have. Just think about a list of numbers that could represent all kinds of things. Like, for example, if you're doing chemistry and you have a sulfuric acid, which is H2SO4, you could think about a vector that represents the number of atoms of each type that you have in some amount of H2SO4. So if you just have one molecule, that would be 2 hydrogens, 1 sulfur, and 4 oxygens, like so. And maybe you want to multiply that by, I don't know, like a mole, whatever, 10 to the 23 power, whatever that big number is. So some really big number k that represents how many molecules of that you have. That would tell you how many atoms you have of each type. And maybe you're like combining this with some number of molecules of water, H2O. So you can imagine why this is a useful kind of thing to do in chemistry, because chemistry involves all kinds of lists of numbers. And the reactions that you do are going to like take some of these compounds and take them apart and put them together into other compounds. So that's just one example I thought of off the top of my head. What's another example? Maybe you have like in social sciences, you're doing data analysis that involves like a list of people or a list of cities or something like that. Or if you're a teacher and you have a list of students in your class, you could think of a vector that represents their grades. Like everybody gets an A on this test. Yay. So if you have 30 students in the class, this would be an R30 vector. And you can imagine, like, what if you wanted to calculate a final grade in the class based on the final exam and the homeworks and quizzes and whatever else? Uh, you can imagine scaling this vector by something like maybe the final exam is worth 30% of the grade, and then 20% of the grade is this other test, and then 50% is other stuff. I don't know. So anytime you calculate grades, you could think of that as vector arithmetic. And of course, that applies to all kinds of other stuff that involves lists of people and data about them. And maybe you can use your imagination a little bit. This applies to all kinds of physics and chemistry and biology and anything else. So yeah, we can think of vector operations, scalar multiplication and vector addition like this, as defined in terms of what do you do with all these components. But it's also important to understand what it looks like with arrows here on the next page to get a visual understanding for how this works. Because a lot of the same principles that we're going to be understanding by like drawing pictures in R2, where it's easy to draw pictures, those same principles can be generalized to R3 or R10 or R30 or whatever. So let's say we have this vector W here. You can think of W as the point, -1, 2, right here. So that is the vector W. Or if you want, you can also think of W as the arrow that starts at the origin and points at that point. And likewise, Z you can think of as the point, 3, 1. Or maybe you want to think of it as the arrow that starts at the origin and points at that point. So there's W and Z. Part B says to draw W plus Z. First of all, let's think of this in terms of the definition with the components. The definition over here says to just add up the components of each. So that would mean doing -1, 2, added pairwise with 3, 1. And -1 plus 3 is +2, 2 plus 1 is +3. So you get this result. So we can just see that W plus Z is this point here, the point 2, 3. But there's a way we want to think of this using the arrows. We can also think of W plus Z as the point you get when you start with the vector W, meaning from the origin go to this point, and then from that point, the tip of the vector W, we're going to connect the tail of the vector Z, like so. And that's visually what it looks like to add Z to W. And that gets you to W plus Z. So let's think for a minute why this works. Well, if you think of W as having these components, -1 and 2, then when we do this version of it, it's like we're taking that -1 and then adding 3 to that, which is like the x component of the z vector. And that 3 is in the x direction. So it's like we're going backwards a distance of 3 from here. So, or you could draw it from this point over there. There's that +3. And so that gets you to that same x component you want. And for the y component, we're starting at w, which has a y component of 2 here, and then we're adding that 1 using the definition with the components. And that 1 is the plus 1 component of z. And so you can see why that works. And also, you could just do it with w as well. If I draw a copy of w from this point, you could do z plus w in this order, and that gets you to the same point. So this is sometimes called like the parallelogram rule for vector addition because we're drawing a parallelogram here. But yeah, it's a good idea to think of vector addition this way when you can, at least in R2. Let's look at part C next. So first, let's just calculate this using the definition with the components. Like, for example, negative 2 times w is defined as multiplying each of the two components by negative 2, which gives you components 2 and negative 4. So where is that? 2, negative 4 is right here. This point is the point negative 2w. Let's keep going with this. The point negative 1 times w is 1, negative 2, like so, which is right here. We can just write that as like negative w. It means the same thing as negative 1 times w. 0w means we're multiplying each of the components by 0, so 0 times negative 1 and 0 times 2, and of course each of those is going to be 0, so that just gives you the 0 vector here. We also have 0.5w, which makes each of the components half as big. And when each of the components are half as big, you get a point that is like halfway closer to the origin, or an arrow that is half as long as w. Likewise, if you do 2w, you're going to multiply each of the components by 2, and you get the point negative 2, 4. And if you think of that as an arrow, that is an arrow that is in the same direction as w, but is twice as long. And same idea with these ones here. We have arrows that are either the same length as w or twice as long as w, but in the opposite direction. So you can see all of these points are on a line, and it's kind of like a number line, sort of like the x and y axes themselves are two number lines. It's just that now we have a w number line that's like scaled differently and in this different direction. So that's another way you can think of a vector, is that a vector is a thing that describes an alternative number line. Let's look at theorem 1.3, some properties of vector operations. This says for all vectors x, y, and z in RC and all scalars r and t, we have the following facts. X plus y is equal to y plus x. So we say that vector addition is commutative, like you can just change the left to right order with addition. Number 2 says you can move the parentheses around when you're doing vector addition. Vector addition is associative. Number 3 says that the 0 vector acts like the number 0, and that if you add it to any vector, it doesn't change it. 4 says that a vector plus the opposite of that vector, and the opposite of a vector, again, really just means negative 1, scaling that vector. When you add those, you will get 0. 5 and 6 here give you two different versions of a distributive rule. This one says that scalar multiplication by vectors distributes over scalar addition. We can distribute that way. And the next one says that scalar multiplication also distributes over vector addition. And part 7 is another kind of associative law that says that scalar multiplication is interassociative with scalar by vector multiplication. All right, so each of these is true because the operations that we're describing when we like add up two vectors or multiply a vector by a scalar, there's real numbers involved everywhere, and these are all familiar properties with real numbers. So to prove them, you basically need to apply the definitions that we have here and show how there's a corresponding property of real numbers. So let's prove one and leave a few others for exercises. So if we're just proving part 1 here, it says that x plus y is equal to y plus x for all vectors x and y. So we want to start by saying, suppose x and y are vectors in RC, but we know any vector in RC is made up of a list of numbers, so let's just label the list of numbers as x1 through xc. And then we want to show that if we do x plus y, it's got to be the same thing as y plus x. So the definition of x1 through xc plus y1 through yc is, this is the vector where all the components are added, like so. Now, each of these components here are real numbers, and we can use what you know about real numbers and say that we can change the order that those are added in. And then that is just the definition of what it means to add the vector y to the vector x. And so we have proven that if x and y are any vectors, then you get the same thing on the left-hand side as the right-hand side. So that's what we wanted to prove. So we have our little end of proof symbol here. Cool. So the other exercises are pretty similar to this with the concept that where you prove other ones of these. I think now is a good time to take a break, and coming up we'll look at lists of vectors and linear combinations of vectors and so on.